Welcome to Chapter 3. In this chapter, we go through most of Yocto's and Bitbake's components in more detail. We will have a mix of slides and terminal exploration, so let's get started. Here is a diagram with which you might be starting to get familiar with. Let's take a second look at the Yocto project architecture and go through the general process Bitbake executes. Bitbake starts by searching the build directory for the conf/bblayers.conf file, which you can open. bblayers. So this file contains a list of folders through the bblayers file, and Bitbake will go through each of these folders and include the metadata that it finds in them. For each directory in the bblayers, Bitbake then searches for the conf/layer.conf file. You can take a look at an example, for instance, in the Meta Raspberry Pi. This file contains, amongst other variables, the bbfiles variable, which basically forms a list of bb and bb-append files, which are the recipes. Recipes form the logic unit of tasks and are written in a mixture of shellcode and Python code. So Bitbake creates an index of tasks it should execute, sorting them in accordance to their dependencies. For each recipe, Bitbake first downloads the sources, and these are downloaded to the path pointed by the dl_dir variable. The sources then are unpacked to the build/tmp/work directory, and patches are applied. We can explore the downloads directory, which in our case we defined to be in a we edited the variable so it would be present in this cache directory. So if we go through the downloads, there's a lot of stuff here. So tar or archives in general are just downloaded to this root directory, so to the parent directory, and they have this done, which is basically a log file saying that the file was downloaded successfully, which means it was checked against a checksum. The Git repositories are all cloned under this git2 directory, so there aren't any name conflicts. The source is then unpacked to the build/tmp/work directory, and patches are applied. It is then compiled and installed into a temporary directory. The artifacts are then copied to the sysroot folder, sometimes being stripped from symbols depending on your build configurations. Finally, packages are generated from the files. For generating the rootfs, Bitbake looks at the list of packages specified in the image install variable and installs those files to the target directory. As we mentioned, Bitbake looks at the image install variable for a list of packages it should include in the rootfs. As long as the package is found in your layers as a recipe, it is compiled, all of the tasks executed, and included in the rootfs. As for the rootfs image, Bitbake looks at the image fs types variable and generates images based on what it finds there. For instance, you can build an ext4 image, a tarball of the rootfs, or in the case of the Raspberry Pi, you have the rpi-sd image, which is a image which is basically prepared to be flashed onto an SD card and includes all of the bootloader, the partitioning, and everything. Image features is another variable which depends on your package, on your distribution rather, and might include several packages. We can take a look at the Pokey case. So you have these features which we already mentioned, like the dev packages, which includes all of the libraries that are specified by your image. So that you can basically then generate, for instance, an SDK, and it will include all of the libraries, so you can develop against it and link using those libraries. The baked images are placed in the build/tmp/deploy/image and /machine, which in our case is Raspberry Pi, as we can take a look. So our machine name is Raspberry Pi, so they're all located inside this folder. In terms of some specific Bitbake syntax or usage, you have the basic usage, which is just Bitbake, and then you issue the recipe name, and Bitbake will only build that recipe. For instance, let's build a Vim. So let's go to our build folder. So Bitbake Vim, in this case it's already built. You can issue a specific command to Bitbake. So in this case, for instance, for Vim again, we can list all of the tasks associated with it, or available to it. This task, oops. So these are all the tasks that are going to be executed for this package or for this recipe. In a similar fashion, you can execute a specific recipe, a specific task for this recipe if you specify the -c and then the task name. Once again, it's already built, so it won't actually do anything. There are also the commands available to Bitbake, which you can investigate using the -h, which is the help command. For instance, this K1 is quite useful. So if you're building an image and one recipe actually fails, but you want Bitbake to build as most as it can, this will just ignore the error and continue building on the other, going through the other recipes or other tasks. The -f command is useful sometimes. For instance, you have a command which is clean S state. So if for some reason you're developing a package and it fails, and you want Bitbake to clear the S state, you can issue this command. It sometimes might give an error, so you can basically just force the command. And it should next time, so this just basically does the do clean tasks, and you can then build the package from scratch. You have other useful commands such as the debug, which shows basically the commands and or tasks that that Bitbake executes. The verbose, which is equivalent to the set -x for bash scripts. So all of the, for instance, BB note messages will appear to standard output. Also for the debug, the BB dot debug messages will appear. So you have also the quiet, the dry run, as we saw previously. GraphViz, which we will see next, it basically shows you the dependencies that a specific task or recipe has, and so on. I think the others are probably not that useful. If you're trying to debug something or just in general see the dependencies that a specific recipe has, you can use the -g, which generates a GraphViz dot file. So for instance, if we want to generate that file for Vim, just do -g. And Bitbake basically dumps the information to this file and the task dependency files. You can use the dot command to convert these files into PDF or PNG, or you can use a utility like a GraphViz viewer. For instance, in KDE you have kGraphView, and what this does is just open the graph. You also have a task explorer, which you can issue with this command, with the -u task exp. And this loads all of the recipes for this image. And this has two views. One of them are the dependencies for this task, and then the tasks which actually depend on this task to be executed first. Let's now go through the folder layout. So we already know the build folder. We have the conf directory, which contains the local.conf and the bblayers.conf file. The build history basically just is a log of the build commands created by Bitbake. Now by default, if you don't specify this download directory or the state directory, you will, by default, those directories are created inside the build folder and have these names. Now the next important directory is the TMP directory, which holds most of the resulting files of all tasks for each recipe, including the compilation artifacts, sysroot, and packages generated. So this is the layout of the TMP directory. In this directory, deploy contains the build products such as the images, packages, and SDKs. The sysroot contains shared libraries, headers, and utilities used in the recipe build process, and work contains the source code, task configuration, logs, and package contents. Now the layout of the work directory is quite important, and it also is generated based on a lot of variables. So package arch is the architecture of the build packages, which varies depending on the destination. We can take a closer look at that. So in this case we have the Pokey. So this is common to all architectures. This is specific to the Cortex, specific to the Raspberry Pi machine, which is a speciality of the Cortex. And these are recipes that are needed by the host to bootstrap or build the other parts of the system. And the last variable is the target OS, and is the OS of the target device, which in this case is mostly Linux. So PN is the name of the package, PV is the version of the package, PR is the revision of the package. So this subfolder here is what in recipes we can refer to as workdir. The bpn-pv directory is what is pointed to by S, and the do fetch and do unpack tasks end up working on this directory, so they unpack the sources to it. The image directory is accessible by the D variable and is normally used by the do install task. Also on the previous one, so we have S, which is referred to by the do fetch and do unpack, and B for the do compile, so where it actually generates some of the artifacts. If the package is split into sub-packages, such as the case is for instance for system D, which contains a lot of components, then we have subdirectories inside this package dest folder, which then repeat the same pattern for this top level directory. Recipe sysroot contains artifacts for the target, and recipe sysroot native for the host. And you also, besides packages, you also have the same scheme for machine, which in our case, Raspberry Pi is an example of that. So this is an example of the first image we built for QEMU. So as we discussed, this contains architecture independent packages, the all prefix. This contains the architecture specific packages for the target machine, and this contains machine specific packages for the customization for this specific machine, the QEMU image which we built. The x86 contains the host sysroot content, so you can cross-compile or develop, so it contains all of the cross-compilation tools necessary. As a practical example, we can look at the grep recipe. So as we saw, this is the package version, package revision, which always has this default value. This is the package without the prefix, so the bpn. And temp actually contains is a good point for debugging. Now let's move on to the local.conf file and specify the common variables that we can see in it. So the machine we've already seen as a target machine selection, download directory, state directory, the tmp directory, which is the build output, the distribution that we will use, which is set to Pokey. If we can take a look at that. So it's set to Pokey. The package classes, which will define the packaging system that you use. So the first, you can have multiple of them, but the first one you define is the one that will actually be used by the package feeds to generate the images and the SDKs. The SDK machine variable defines if you specify Bitbake to build the SDK, it's the target machine for which the SDK is built. And this extra image features is defined normally by the distribution. It's basically groups of packages that you can choose. So as we mentioned or hinted previously, the recipe naming is normally package name underscore package version. So since it uses this underscore to parse these two variables, you can't use underscore as part of the package name. You can also specify a wildcard. For instance, if you're doing an append recipe and you want to make that recipe apply to all or irrespective of the actual package version, you can just specify a percentage signal, which will be replaced by whichever version Bitbake then takes on. Additionally, inside the recipe file, you can also specify, regarding the package versioning, the package epoch, which the default value is 0, and the package revision. So these are the variables that you'll normally find inside a package. You have the source URI, which lists which is a list of files or patches or the sources or the repos of the package the recipe that you're building. As an example, this is a get URI. For the get URI, you can specify the branch, which isn't needed if you're using master. You can also forget, for instance, you have to specify the source rev, which is the commit hash. If you have binary files, you also need to specify the checksum for them. This is normal also for licenses. So in this case, imagine that in the source URI, you have a file named file name. So you'll have to use this syntax in order to specify a checksum for that file. The depends variable lists the dependencies that the package has for building, and the rdepends is the list of the runtime dependencies of those packages. Additionally, you can implement methods such as do install, do patch, do compile, all of the tasks that are normal to Bitbake. So you can either append to them, specialize them. If you, for instance, create a method named do install underscore Raspberry Pi, it will only be executed for the machine which is named Raspberry Pi. So here also worth mentioning is that rdepends is important for the package manager, so it knows the dependencies when it needs to install a package. Let's go on to see an example for a recipe. So you have these additional fields that we didn't specify in the previous slide, the summary, which is just a text description of the package, the license, and the license checksum, so that no one tampers with the license, which for commercial cases is important, not for our case probably. The source URI, so here you see a list of files including this the license file. And in this case, the source is actually included in the package itself, or the package, the recipe directory. But this is something that you actually shouldn't do because it goes against conventions, which a layer should only contain metadata or patches, not the actual sources. But this is just an example. So in this case, you're specifying DS directories like we mentioned previously, and as an example, we have the do install method, which is So by default, the do compile just calls make, so we didn't need to specify that. But the do install is installing the binary, which will result of the make command, into the bin dir, and we can see what this variable points to next. As we mentioned, this is the install path, local to the recipe, and so it creates a directory if it doesn't exist, and then it copies the file or installs the file with these permissions to that directory. If you want to get more information to where these variables actually point to, you should check the bitbake.conf file, and in this case we can see how they are defined. For instance, the sysconf dir is just etc. Where is bin dir? Bin dir is just bin/bin. This is just a prefix, which obviously points to the sysrootfs or some install path. Sbin dir, the library dir, which is a baselib. It should be just lib/lib. Baselib, here it is, and so on. Now, we haven't specified the actual code syntax. We can do that now by visiting this URL. So functions are specified just as commonly we do in Bash keywords, so you can export them. Inherit is, so it looks for this file, and if it finds it, it includes it. Require, on the other hand, gives an error if it doesn't find this file. So comments, so you prefix the line with a hash. Line continuation, just like in Bash or in make files. Variable expansion, just as like in Bash. And you can find all of the rest of the syntaxes. So, for instance, the conditional assignment. So this question mark equals only assigns a value to this variable if it hasn't been, if it's currently unset appending. So you have two ways of appending to a variable, which is using this notation, the plus equals, but this only this specific notation only appends if the variable already exists. So it's to existing variables. If you're not sure if the variable exists, you can just use underscore append, which is this one. But you have to be careful because this will concatenate. It's like string concatenation, so you'll actually have to add the space before actually including something. We also have prepend and so on, overrides, Python code. So you can actually inline Python, as you can see here. Right. So as we just mentioned, you can also include Python code in your recipes. So this is a normal Bash style method, and this is a Python method, so you basically just need to prefix the method name with the keyword Python, and then you can use normal Python code. Now, in terms of packaging, Bitbake supports RPMs, debs, IPKs, which is from the open package format, and just simple tars. And these are specified by the package classes variable in your local.conf or in your image layer, which we will see in the future. So that's it for this chapter. On the next chapter, we will start by creating our own recipes and layers to create our own customized distribution. See you then.